In this module, we will be talking about the breakdown of the Born-Oppenheimer approximation, selection rules for rotational vibrational transitions, and finally PR branches. After going through this module, you should be able to firstly use the Born-Oppenheimer approximation to understand the effect of rotational transitions on vibrational spectra, understand the breakdown of this approximation and interpret the observed spectra, and finally use data from real vibrational spectra to obtain fundamental vibrations and rotational constants. So, a brief introduction. The vibrational spectra of diatomic molecules is expected to show a few lines corresponding to the fundamental and a few overtones, precisely the first and second overtone, as well as a hot band corresponding to a transition from the excited level. However, the gas phase spectra are more complicated than this, and the distinctive shape of the contours give us more information about the molecule. First, we will talk about the breakdown of the Born-Oppenheimer approximation. When we consider pure vibrational or pure rotational transitions, we assume that the two are independent of each other. This is essentially the Born-Oppenheimer approximation, which states that since the energies involved are very different, they do not interact. That means vibration does not interact with rotation, you can treat them separately, and this is what we have done. We studied rotation first, and now we have studied pure vibrational spectroscopy. Now, suppose you consider a molecule that is simultaneously undergoing vibration and rotation. The rotational energy levels separations are of the order of 1 to 10 centimeter inverse, and we have already seen that the vibrational energy level separations are of the order of 3000 centimeter inverse. So, to a good approximation, a molecule executes rotational and vibrational motions independently, separately from each other. And according to the Born-Oppenheimer approximation, the total energy of such a molecule, where you have two independent kinds of motion, can be written simply as a sum for the rotational and vibrational energies. That is, that the total energy is a sum of E rotation plus E vibration. So, if you express in wave number terms and you express the total energy in terms of whatever we have learned up till now, what you find is that S, which is the vibration rotation term and depends on two quantum numbers V into J is equal to B bar into J plus 1 minus the centrifugal distortion term D bar J square into J plus 1 square, and then you have the vibrational energy, which is V plus half omega E minus chi e omega E V plus half square. So, all these terms, they are in centimeter inverse. The rotational constants are much smaller than the vibrational frequencies, and the centrifugal distortion constants are even smaller, and so you can ignore the centrifugal distortion constant and remove the d bar term, because it is much smaller than the vibrational energy term, which is the dominating term, and but obviously you have to keep the B bar term, and so the total energy is B into J plus 1 plus V plus half omega E minus chi e omega E V plus half square. Now, the selection rules for the combined rotation vibration terms are similar to those for the individual transitions. That means, for delta J you can have plus or minus 1, and delta V can be plus minus 1, plus minus 2, plus minus 3 in decreasing probability. So, if you want to derive an analytical expression for the spectrum, you can obtain by applying the selection rules to this equation, and you consider only the V is equal to 0 level, because we have seen that this is the only one which has the maximum population, and J can have any value, and we consider a transition from V is equal to some J value, and which is equal to J double prime, and to another V value V is equal to 1, this is the fundamental transition, and to a rotational level J prime. We are considering a transition where the ground state is V is equal to 0 and the rotational level is denoted by J double prime, to another level V is equal to 1, this is a fundamental transition, and the J value is given by J prime. Now, it is customary in spectra to use a double prime for the ground state and a single prime for the excited state, and this is what we will be doing all the time. And how do we find out the transition energy? By finding out delta S J V is equal to S J prime 1 minus S J double prime 0, the excited state minus the ground state is equal to B bar J prime into J prime plus 1 plus 3 by 2 omega E minus 9 by 4 omega E chi E, and minus the energy of the ground state, that is B bar J double prime plus 1 plus half omega E minus 1 by 4 omega E chi E, and this simplifies to omega E into 1 minus 2 chi E plus B bar J prime minus J double prime multiplied by J prime plus J double prime plus 1 omega 0 plus B into J minus J double prime, J prime plus J double prime plus 1, and here we have substituted omega 0 is equal to omega E multiplied by 1 minus 2 chi E, and this we have already seen is the energy of the fundamental. Now, since the transitions which are allowed are delta J is equal to plus minus 1, and we are considering absorption spectroscopy, we will assume that delta J is equal to plus 1 and J prime then becomes equal to J double prime plus 1, and when you substitute that you get an expression for the transition frequency. Now, when delta J is equal to minus 1, when there is a decrease in the rotational energy, in that case J double prime is equal to J prime plus 1, you get a similar expression in terms of J prime. So, we combine both these terms, and instead of J prime plus 1 or J double prime plus 1, we write down M, and because the sign before that is different for the two equations, we allow M to take on all integer values which can be positive or negative, and that means M can be plus minus 1, plus minus 2, it can be any one of these, and omega 0 plus 2bm is the transition frequency, and omega 0 is known as the band origin or band center. Now, this equation represents the combined vibration rotation spectra. It will consist of evenly spaced lines, and where the spacing is equal to 2b bar on each side of the band origin, and which is omega 0, but since M cannot take on values equal to 0, that means that the band origin at omega 0 will not appear. Lines at the low wave number side of omega 0, where M is negative, that is that delta J is equal to minus 1, there is a decrease in the rotational energy, are referred to as the P branch, while those to the high frequency side for which M is positive and delta J is equal to plus 1, there is an increase in the rotational energy, these are referred to as the R branch, and this we have shown in the figure, gives a schematic diagram showing the P and R branches of a diatomic molecule. Lines on the left side are the P branches and those on the right side are the R branches. The band center is missing. So, this is what we had derived, that the band center will be missing because delta J cannot be equal to 0, but there will be lines at the low frequency side of the band origin which correspond to delta J is equal to minus 1, and on the high frequency side they will correspond to increase in rotational energy and delta J is equal to plus 1, and these are respectively known as the P and R branches. Also, it is clear that the band center is the average of by P1 and R0, this 1 signifies from which rotational level the transition has occurred. So, that means P branch, it is the transition from J double prime is equal to 1 to J prime is equal to 0, and you have already seen that delta J is equal to minus 1 for the P branch. Now, an R branch can start from 0 also. A P branch cannot start from 0 because this would imply that delta J is equal to minus 1, it has to go to the minus 1 level of the excited state, which is not possible because J can only have positive integer values starting from 0. So, but R1 is possible, it can take place from J double prime is equal to 0 to J prime is equal to 1 because delta J has to be equal to 1. Now, we have given in table part of the IR spectrum of carbon monoxide, and you see that the band center is at 2143.255 centimeter inverse. We have obtained from P1 plus R0 the average of this, and the average line separation near the center is 3.83 centimeter inverse, and because you know that the spacing is approximately equal to 2b bar, this is equal to 3.83 centimeter inverse, and you can see that b bar is equal to 1.915 centimeter inverse. Now, this is the IR spectrum of carbon monoxide, where the line at P1, P2 and P3 are at 2139.43, 2135 0.55 centimeter inverse and 2131.63 centimeter inverse. You can calculate the separation between these lines. Similarly, there is a line at R0, R1, R2. The first three R lines are at 2147.08, 2150.86, 2154.59 centimeter inverse, and their separation between R0 and R1 is 3.78 and the separation between R1 and R2 is 3.73 centimeter inverse. The average of P1 and R0 gives you the band center and the average spacing gives you the 2B bar value. Now, the value that we have obtained is in satisfactory agreement with the more precise value that was obtained from microwave spectroscopy, pure rotational spectrum, and this was 1.92118 centimeter inverse. There you obtained it to very high degree of precision, but here also you got a very almost same value, and from this value of V bar the moment of inertia I and the bond length can be determined. So, this is the example. The four central lines in the high resolution B is equal to 0 to V is equal to 1. It is also customary in spectroscopy to write the excited state first, and infrared spectrum of HCl, where we have specified that the isotope of chlorine is 37, occurs at 2837.6 centimeter inverse, 2858.8 centimeter inverse, 2899.2 centimeter and 2918.6 centimeter inverse. So, you are required to deduce as much as possible about the molecule, and would you expect the lines for H, the normal isotope of chlorine 35, to lie at the same spectral positions. The band center is at the average of the two central lines, that is, it turns out to be 2879.0 centimeter inverse, and so this is equal to the fundamental frequency omega 0. The separation at the center is 4B bar, 2B bar on each side, and this is 40.4 centimeter inverse. That means B bar is equal to 10.1 centimeter inverse for B. The moment of inertia is equal to I is equal to h by 8 pi square B bar C, and this turns out to be 2.771 into 10 raised power of minus 47 kilogram meter square. The reduced mass you can find out in the usual way, m1 m2 by m1 plus m2 divided by Avogadro's number and multiplied by 10 raised power of minus 3 as we have been doing, and this is equal to 1.629 into 10 raised power of minus 27 kg. So, that means you can find out the value of R, because I is equal to mu R square, R is equal to square root of I by mu. You substitute both the values and you find that R turns out to be 1.304 into 10 raised power of minus 10 meters, and which is equal to 0.1304 nanometer. So, you have accurately determined the value of the bond distance of carbon monoxide by looking at its vibration rotation spectrum. So, since the positions of the lines depend on the reduced mass, the lines for HCl with the normal isotope 35 chlorine will be at a different position. The reduced mass of H35Cl is smaller, and hence its moment of inertia is smaller and rotational constant is larger. So, the lines will have larger separation. The fundamental vibrational frequency will also be higher, since it is inversely proportional to the square root of the reduced mass, but the bond length will be the same. Now, we will discuss the interaction of rotations and vibrations. So, according to this discussion that we have had just now, the rotational spacing should be the same. However, this is not the case. A crowding of lines is seen in the R branch with increasing J, whereas the spacing increases in the P branch. Apparently, the assumption of independence of vibration and rotation is in error, and there is an interaction between these two forms of energy. Since the frequency of vibration is higher than that of rotation, a molecule vibrates 1000 times during the course of a single rotation, and so the bond length and hence the moment of inertia I and also B bar also changes continually during the rotation. The rotational constant B bar depends on the average value of 1 by R square. It does not depend upon the average value of R, because B is inversely proportional to I, and I is equal to mu r square. So, it depends upon 1 by r square, the average value. Further, an increase in vibrational energy is also accompanied by an increase in the vibrational amplitude. You see that it keeps on getting wider, the potential energy well, and because of the widening of this potential energy well, the value of B bar will depend upon the vibrational quantum number also. So, you see an interaction between vibration and rotation. This increase is even more pronounced for anharmonic vibrations, where the widening of the potential energy well is even more. An increase in vibrational energy will lead to an increase in the average bond length. The vibrational constant then varies even more with vibrational energy. In general, since the equilibrium internuclear distance R average increases with the vibrational energy, it is B bar is smaller in the upper vibrational levels than in the lower ones. We may express this dependence in terms of an empirical equation. B is equal to B E minus alpha into V half, where B V is the rotational constant in the vibration level V, B is the equilibrium rotational constant at the potential minimum, and alpha is a small positive constant. So, consider the fundamental vibrational change from V is equal to 0 to V is equal to 1. The respective B bar values will be B0 and B1. For this transition, then we can find out the wave number nu bar. It is given by the difference between G, the vibrational term, J prime B is equal to 1 minus G, J double prime B is equal to 0, and this gives you omega 0 plus B1 J prime into J prime plus 1 minus B0 J double prime into J double prime plus 1, and where we have substituted omega 0 is equal to omega E into 1 minus 2 chi. So, we now have two cases. One is the allowed transition delta J is equal to plus 1, where the upper state J prime is equal to J double prime plus 1, and if you substitute the values, what you find is that the wave number of this transition is given by omega 0 plus B1 plus B0 into J prime plus 1 plus B1 minus B0 into J double prime plus 1 whole square, and where J double prime can take on values 0, 1, 2, and they are the initial values. Now, case 2 is when you have a rotation emission delta J is equal to minus 1. In that case, J double prime is equal to J prime plus 1, and when you make this substitution, you find that the wave number is equal to omega 0 minus B1 plus B0 into J prime plus 1 plus B1 minus B0 J prime plus 1 whole square, and J prime can take on values 0, 1, 2. So, we can combine both these equations because they are similar. In one case you have J double prime, the other one you have J prime, and we write down that the wave number of a PR band is given by nu omega 0 plus B1 plus B0 into M plus B1 minus B0 into M square, and M can take on values plus minus 1 plus minus 2 because it is equal to J prime plus 1 or J double prime plus 1, and the lowest values of J prime or J double prime are equal to 0. So, the positive M values you can see refer to the M R branch, and the negative ones they refer to the P branch. Now, this equation allows us to fit the observed transitions to a quadratic equation from which the various terms can be determined. Now, since B1 is smaller than B0, because the internuclear separation is higher in the higher vibrational states, the spacings in the R branches decreases with increasing J, and the opposite is observed for the P branches, and this gives a distinctive shape to the spectrum. And this is what we have learnt in this module, that the rotation and vibrations are not independent of each other. And in summary, an approximation that can be used to understand vibration rotation spectra is the Born-Oppenheimer approximation, which states that since the energy scales are different, the two motions can be treated independent of each other. The two selection rules also remain the same. Application of the selection rules predicts two branches in the spectra, but the band center itself is missing. However, analysis of the spectra yields information about the vibrational frequencies and rotational constants, and all corresponding molecular parameters can be determined. However, analysis of real spectra shows a crowding of lines at the higher wave number R branches and a spacing out of the P branches with increasing J. This implies that the rotational constant is not independent of the vibrational quantum number and decreases with increasing V, since the average bond length decreases with increasing amplitude of vibration.